In this video, we're going to do some extra examples about Markov chains and computing kth state matrices in the future. So, consider a Markov chain with the transition matrix given below. So P is 0.1, 0.9 in row 1, 0.6, 0.4 in row 2, and the states are A and B in that order. So our rows are labeled A, B, columns also labeled A, B for the matrix, and for the initial state S0. So this means, since the probability here for A is 1, it means that the process definitely begins in state A. Okay, what we want to do here is compute S4, okay, so the fourth state matrix, recursively and then using powers of P. So we're going to do it in two different methods. So remember, the recursive method is that you're going to compute Sk by taking the one before, Sk minus 1, and timesing by P. So we're going to have to compute S1, S2, S3 before we can get to S4. Using powers of P, we're going to use the formula that Sk is the initial state S0 times P to the power 4. So there we're going to have to compute powers of P. So let's do the recursive one first. Okay, so we'll start with S1. So that's going to be S0 times P. So that's 1, 0 times 0.1, 0.9, 0.6, 0.4. Okay, now when we do this, we take this row by this column. That's going to give us the first entry. And then we take the same row with the second column, and that gives us our second entry. So here we're going to have 1 times 0.1 plus 0 times 0.6. And then we're going to have 1 times 0.9 plus 0 times 0.4. So S1 is going to be 0.1 and 0.9. And that makes sense because we're definitely in state A. So the probabilities that we go to A or B is given by row 1, okay, in the matrix, and that's what we got. So now we want to compute S2. So this is doing S1 times P. Okay, so we take our new S1 and we multiply by the transition matrix, okay, using the same method. So we're going to have 0.1 times 0.1 plus 0.9 times 0.6 for our first entry. And our second entry doesn't really fit here. I'm just going to go down a bit. 0.1 times 0.9 plus 0.9 times 0.4. So that's 0.01 plus 0.54, and then 0.09 plus 0.36. So we get 0.55 and 0.45. Now notice, you can tell that you've done it right, or hope a good sign that you've done it right is that your probabilities that you get should add to 1. Okay, so this one plus this one equals 1, so we think probably we're right. Okay, now we already did S2. S3, we take S2 times P. Okay, so I'm going to write this one out a bit less. So if you take S2 and you multiply by P, you're going to get 0.325 and 0.675. So again, they add to 1. And then S4 is going to be S3 times P. So we take this one and we multiply by P. And then we're going to get 0.4375 and 0.5625. So this is our S4. Okay, so then using powers of P, S4 is S0 times P to the 4. Okay, so we need we need to compute p to the power 4. So we're going to start by computing p squared. So that's taking p and multiplying it by itself. Okay, so row 1 times column 1 gives us this entry here. So 0.1 times 0.1 is 0.01, plus 0.9 times 0.6 is 0.54. Okay, and then we're going to take row 1 times column 2, and that's going to give us the entry in row 1, column 2. So 0.1 times 0.9 is 0.09. 0.9 times 0.4 is 0.36. Okay, and then we have row 2, do the same thing. So 0.6 times 0.1 is 0.06. 0.4 times 0.6 is 0.24. And then we have to do row 2 in column 2. So 0.6 times 0.9 is 0.54, plus 0.4 times 0.4, which is 0.16. So for p squared, we're getting 0.55, 0.45, and 0.3, and 0.7 for row 2. Okay, now we can skip P3 and go straight to P4. Okay, so P4 is going to be P squared times P squared. So we're going to take the matrix that we just got and multiply it by itself. Okay, so if you do that, you're going to get 0.4375 and 0.5625 in row 1. And in row 2, sorry, it's 0.375 and 0.625. Okay, so that's p to the 4. So that means S4 is S0 times this matrix p to the 4. So that's 10 times this matrix. Okay, and when we do that, so when we take this row times this column, the 1's going to hit the top entry and the 0 is going to not. So we're not going to add the second thing. And then same thing over here when we do that. So this thing is going to be just the top row of this matrix. Which makes sense, again, because p to the 4 is the probability that I go from A to B. So each entry, depending on which row and column it is. So for instance, this entry here, 5625, is the probability that I go from state A to state B after 4 steps. Okay, so because our S0, we definitely start in A, we're going to want to take that row because it tells us what happens for things that start in A after 4 steps. Okay, and notice that this is the same as above. Okay, so it doesn't really matter which method you use. I prefer the first method unless I have to go really far. Okay, so then this one can be faster because you can jump certain powers of the transition matrix. So let's do one more example. So suppose you're planning to play rock, paper, scissors, and you know that your friend usually picks depending on what they picked before. So the rules they follow are after rock, okay, after they pick rock, there's a 70% chance they play rock again, 20% chance they play paper, and a 10% chance they play scissors. After they play paper, they only play paper or scissors next, and they pick at random. After scissors, there's a 30% chance they play rock, 70% chance they play scissors. Okay, and you know in the first round that they select at random. So, well, you want to know what you should play in the second round so you're more likely to win. So we want to figure out what they're likely to play. So the states here are going to be rock, paper, or scissors. Okay, so I'm going to call this R, P, and S. Okay, now the transition matrix, let's call it T so that I don't use P twice. So it's going to be a 3 by 3 matrix. So I'm going to label the states in that order. Otherwise I might get confused because I always say them in that order. So remember that these ones are the current state and these ones are the next state. So when we enter the probabilities, it's going from the row state to the column state. So in row 1, we want to use after rock. Okay, so these probabilities are going to go in row 1 because that's where they played rock in the current state. So this is the chances what they play next. So there's a 70% chance they play rock next, 20% chance they play paper, and a 10% chance they play scissors. So that row is going to be 0.7, 0.2, 0.1. Okay, after paper, that's going to be what goes in row 2. Okay, and they play paper or scissors and pick at random. So that means that they're equally likely. Okay, so at random implies equally likely. So there's a 50-50 chance they pick paper or scissors. So that's going to be 0.5 and 0.5, which means this one, rock, has to be 0. They never play rock after paper. After scissors, okay, this is going to go in row 3. So there's a 30% chance they play rock, a 70% chance they play scissors. That already adds to 100%, so that means they never play paper after. Okay, so there's our transition matrix. They also told us S0. Okay, so how did we know this? So you know in the first round that they select at random. Okay, so S0 is what's happening in the first round. So if they select at random, I'm going to write it as a fraction because it's 0.33333, but there's going to be a 1/3 chance that they pick any of them because they pick at random. Okay, so we want to know what happens in round 2. Okay, so let's just make a note that S0, this is actually round 1. So what we want is S1. Okay, so S1 is the second round. So we're going to take S0 and multiply by our transition matrix, which I called T to avoid the P for the paper. So that's going to be 1/3, 1/3, 1/3 times our matrix. Okay, so I'm going to get a 1 by 3 matrix. So it's going to be for the first entry 1/3 times 0.7 plus 1/3 times 0 plus 1/3 times 0.3. So that's doing this row by this column. Okay, that gives us that entry. Then I'm going to have 1/3 times 0.2 plus 1/3 times 0.5 plus 1/3 times 0 for the second column. Okay, and then I have one more column to do, and I'm going to go down a bit so it fits better. Okay, so 1/3 times 0.1 plus 1/3 times 0.5 plus 1/3 times 0.7. So that's this row by this column gives us that entry there. Okay, so if we compute these, the first one is 10 out of 30, or 1/3. Okay, so I'm converting them to fractions. So for instance, 0.7 is actually 7 out of 10. This is a 0, so it doesn't matter. And this is 3 out of 10. So 1/3 times 7 out of 10 is 7 out of 30 plus 0 plus 1/3 times 3 over 10 is 3 out of 30, so I get 10 out of 30, which is 1/3. Okay, I mean, you can use your calculator here, it doesn't really matter. So similarly, the second entry is going to be 7 out of 30, and the third entry is 13 out of 30. If you want to compute these to decimals, okay, it's 0.33, 0.23, and 0.43. Okay, if you wanted to compare them using fractions, you just want to write this one as 10 over 30 so that they have all the same bottom, because then you can easily tell that this one is the biggest. Okay, but if you do decimals, you can tell that as well. Okay, so then remember that our states go in the order rock, paper, scissors. So that means your friend is most likely to play scissors in round 2. So you should play rock, because rock crushes scissors, okay, to maximize your chances to win.